over the field F, and field F is some local non-Archimedean field. So for us, for example, it can be Fq of t. And local Lagrange is about the smooth, irreducible, complex representations V of the group G of F. So let me denote this set by star. And so local Lagrange studies these irreducible complex representations. And let me recall that smooth means that there is a fixed vector in V with respect to some I inside G of K that is open and compact subgroup. And in this talk, we will specify our I, namely for us, I will be the Ivachori subgroup, which is defined as follows. You take the preimage of B of Fq, where evaluation at 0 is the homomorphism from G of Fq of T power series to G of Fq. Just evaluation at 0. And then you take upper triangular matrices here and take their preimage. So this will be I. Okay, so the claim number 1 is that if you consider this set star with respect to this particular subgroup here, this Ivachori subgroup, that then these particular irreducible representations identify with the set of irreducible representations of the following algebra. You consider locally constant functions with compact support on G of F, which are invariant with respect to I on the left action and I on the right. And the algebra function, this algebra structure here is given by the co-multiplication. Okay? And this algebra actually can be described explicitly. This algebra is so-called affine Hecke algebra that I denote by HQ of W hat, or sometimes just by H. And this will be sort of like the main algebraic object of the talk. And how it appears in the general picture, irreducible representations of it control these guys for Ivachori subgroup. Okay, so now let me describe this algebra for you. Let me do it here. Right, so this algebra H, this is just the span over C of certain elements that are known by TW, called so-called standard basis. Here, they are labeled by W hat. And let me recall that these TWs will be just the characteristic functions of Ivachori orbits of the elements of a Weyl group. And you can explicitly compute the relations between them, namely, when you multiply TW1 and TW2, you get their product if the length of the product was equal to the sum of lengths. And the second relation, again, that you can just read off from SL2 computation is the following. So this is so-called Hecke relation. This is equal to 0 for every S, which is a fine simple reflection. Okay, so yeah, any questions so far? Right. Okay, so what is important about this algebra? So in principle, yeah, let me make a comment. So this definition makes sense for any Coxeter group. And here Q can be any number, not necessarily a power of P. And you can also consider Q as a variable that we will do later on. But what is so special about affine Hecke algebra is that it has an alternative realization called Bernstein presentation, which will be crucial for the talk. So right, so and what is like important, so already if you just consider W hat without any deformation, you can identify it with the direct product of a finite while group and Q check, where Q check is the core-root lattice for your group. And similarly, H is generated by certain element that I denote by theta gamma, labeled by core-roots, and TWs coming from this finite W. And what's important here is that these guys form a commutative subalgebra. So they commute with each other. And so from this, what we see, so for example, if you consider this group algebra of W hat, so you put Q equal to 1, then this algebra contains a subalgebra, functions on Q bar, W invariants, and this is already central here, right? So this is central commutative subalgebra, and this algebra as a module over this algebra is finite. So and the same thing happens for H. So this implies that irreducible representations of H are actually finite dimensional. Okay? Okay, any questions on this? Right, so now let me recall you the description of this irreducible representation, so about this star I. And this is the result of Kazhdan and Lusztig. And before doing this, we need some, yeah, I can use this. Yeah, you can use this one more. Oh, okay. Yeah, let me now use this one. But this one, it will become, okay. I think if you want, I can just use these two, whatever you prefer. If for you it's easier to, yeah, okay, let me just use these two. Okay, so yeah, let me recall this theorem. Okay, so first theorem, due to Kazhdan and Lusztig, claims that this algebra H has a geometric realization, and it works as follows. So it's isomorphic to the equivariant K-theory with respect to G check. So here I put the Langlands dual group, and I have C star, which corresponds to my Q variable. And here, what should I consider? I should consider N tilde cross N tilde over N. People call this Steinberg variety or variety of triples. And the product on this algebra will be given by the convolution product, as always. And let me recall these guys. So this N tilde is T star G check mod B check, which you can identify with pairs X and B, and X is in the important radical of B. As always, and this map is a resolution of singularities, just forgets B. Okay, so-called Springer resolution. Okay, so this is the theorem, and let me maybe just make a comment that, like, how it works. So if you take this theta gamma element here, then it will correspond to some particular, like, line push forward of certain line bundle on the diagonal for this N tilde. Namely, you take a line bundle on G mod B corresponding to gamma, you pull it back to N tilde, and then you push forward via the diagonal map. So what is the theta gamma? Theta gamma is a certain generator, yeah, that I already erased. So the generator of H corresponding to this realization of W hat is a semi-direct product of W and Q check. So this is like, and gamma is an element of Q check. So we had this realization of W hat as a semi-direct product of W and Q check. and then it sort of deforms to the realization of H. So H will be spanned by the group algebra of W and certain element theta gamma check, which sort of correspond to this. So these guys, what is important about them, they commute with each other. And obviously, like line bundles commute with each other when you tensor. If, so it works as follows. If gamma is, say, anti-dominant, then yes, but in general you should divide. In general you should write gamma as a difference of two anti-dominant weights, and then you should divide one t by the other t. Yeah. Okay, yeah, and let me say that simple reflection here go to some very particular correspondences supported on some. Not obvious, but you can prove this. Yeah. From this, I mean, from this perspective, yes, you just tensor two line bundles, right? Yes, 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 but it acts on K-theory of untilde faithfully, so you can. Yeah.
So that's because it's on the diagonal?
Yeah, and they all on the diagonal, right? Mm-hmm. Okay, so now let me make the actual like theorem describing. So this is like geometric realization of our algebra and how to use it to obtain the parameterization of simple objects. So theorem number 2, which is again due to Kazhdan and Lusztig, and slight generalization of it due to Xi. So let me formulate it, but first of all let me make some notation. Let Pw of Z be the following sum. L is the length for just W, not affine W. So more or less this is an earlier characteristic of G mod B. Just formal sum depending on Z. And let's make the assumption that Pw of Q is not equal to 0. Then irreducible representations of our HQ are in bijection with the following triples, E, S, and ρ, where E is the element of the nilpotent cone, S is some semi-simple element in G check, such that SE, S inverse, is equal to QE, and ρ is the irreducible representation of the centralizer inside G check of the pair E and S modulo the connected component. So this is some additional piece of structure that you don't see, don't see for G equal to GLN. Because in case of G of GLN, these centralizers will always be connected. Okay, so let me now say like how this works sort of explicitly, namely how to associate to such a triple representation. And then I'll try to explain like why you should expect a statement like this. Right, so we have this triple.
Sorry, is that PWQ non-zero assumption or is it a conclusion?
Assumption. This is the assumption. So when Q is some particular, yes, when Q is a root of this PW, this theorem, as stated, doesn't work. Of course, if Q was a power of P, which is interesting for local Lagrange, then this will always be true. But in general, representation theory of HQ at roots of unity, some particular roots of unity, is more complicated. Right, okay, so how it works, so we start from this ES rho, and then we associate to it the following module over our convolution algebra. You take a K-theory of BE S rho. So what is this? So BE is just the Springer fiber. Namely, we have our nilpotent E here. We can consider the fiber over this nilpotent here. Now S acts on the Springer fiber and we pass to fixed points. And then just from the general story, convolution algebra acts on this guy without ρ. But note that on this K-theory, we also have an action of this quotient that I denote by AES. Of course, connected groups act trivially on K-theory, but this group is already disconnected. So you have this action, and this action commutes with the action by convolution. So what you can do, you can pick an isotypic component corresponding to some irreducible representation. Okay? And now, so this module is not irreducible in general. It's called standard module. But the claim is that this standard module has a unique simple quotient, the unique simple quotient. And this is the one. So this is the unique simple quotient. And this is what corresponds to this triple.
So where does the little s take value?
Yes, little s is an element of G check, semi-simple element. Let me put it here, s in G check, semi-simple. Right, great point. So I should write here that rho is admissible. Thank you very much. And admissible precisely means that this thing is non-zero. So actually in this correspondence, you see only like certain subset of rows which are admissible. Okay, great. So let me now try to explain like why this sort of happens.
Can you repeat again? So E sub E is a fiber, E sub E superscript s.
Is a fiber of this map.
Is what?
Fiber of this map.
S, okay.
And S is fixed points of this. Yeah.
And then you take the K.
K-theory of this variety
The subscript row is
corresponds to taking isotypic component. So yeah, let me say that K-theory of this BES on this guy, on this vector space, you have an action of this component group. So just the centralizer of E and S, of course, acts on this variety, and the action of it factors through the component group. And now you can consider this as a module over this finite group. And you can decompose this as a direct sum of over irreducible representations. Exactly. Row tensor isotypic component, right? And now your convolution algebra commutes with action of convolution algebra commutes with this decomposition. So it acts on each piece. Okay, so now let's see like why this works.
If we're in type A, is Steinberg going to be something?
So Steinberg always,
Or,
if we're
related to Coulomb branches or things like that, or fixed branches, it's unknown.
I mean, n tilde will be a Coulomb branch. In type.
But Steinberg itself is not.
Yeah, well, it's this G mod B, and you have new column.
So this, yeah, this natural correspondence.
Oh, I see.
Yeah.
It's a correspondence.
It's a correspondence. Yeah. Okay, so yeah, let me now. So let's now assume that Q equal to 1, okay? I'll try to explain to you why we get this parameterization. So if Q is equal to 1, as we discussed, W hat is the semi-direct product of W and Q check, right? So very simple group. And this is just a direct product of finite group and the lattice. So we know how to describe irreducible representations of this group by Mackay theory. Namely, we know that irreducible representations of W hat are in bijection with pairs chi and V, where chi is the character of our lattice, and V is the irreducible representation of the stabilizer of this character inside W, that I denote by W chi. And how this explicitly works, you start from this pair, and the corresponding irreducible representation will be the following. You induce from the semi-direct product of W chi and Q check to our W hat the following module. So you just take V with an action of W chi on it, and Q check will act by the character chi. So this is just the very standard theory of how irreducible representation of semi-direct products with the lattice look like. Okay? But now, so we have this description, and now let's see how this is compatible with what I said. Because let me make a comment that this description doesn't really depend much on Q. For example, this variety does not depend on Q. Right? Okay, so let's relate them. Okay, so we assume that Q is equal to 1. This means that S and E literally commute with each other. And the module that we want to consider there is this K theory of BES rho. Right, and now, okay, let me recall for you that if you're just dealing with flag variety, and you're taking a fixed points of the flag variety with respect to some semi-simple element, then what you get just a disjoint union of flag varieties for L, labeled by W mod WL, where L is the centralizer of S connected components at G check, right? So like very standard fact. If you take flag variety, take fixed points of it, you get just a union of flag varieties for the smaller group. And now the same thing holds for this BES. So this procedure is compatible with passing to the fiber over BE. Namely, this BES will be the disjoint union of the Springer fibers, but for the smaller group L. So this means that the K theory that you consider is actually the K theory of disjoint union. So it's just a direct sum labeled by this quotient. And of course, this is compatible with the action. And actually, this K theory is just isomorphic to the induced representation from WL hat to W hat. And here you consider K theory already of BLES. And know that S is central in L, so it doesn't really change this variety. It only corresponds to the action of Q check. Okay, so we see that our module is isomorphic to this guy, and now we want to study, we want to find irreducible quotient of it. So now let's look at this K theory. So this K theory is a module over WL, and in this K theory you have a filtration by support, which is compatible with the action. So what you can do, you can take a quotient from this K theory to the H top of BLES. So this will be a quotient of your module. So this induced module has a quotient being induced from WL hat to W hat from this guy. And everywhere I should put rho. And now let's look at this guy. This is a module over WL. And here we're considering top components of the Springer fiber. So the classical Springer theory tells us that this will be the irreducible module for the finite Weil group. And the action of our lattice is directly via this S, considered as a character. So in this way, we arrive, so this means that this chi literally corresponds to S, and this choice of V, representation of WL, corresponds to a choice of a nilpotent and rho, as in the classical Springer theory, finite dimensional for W. Okay? So yeah, so the point here is that this description is very natural, so you just sort of glue together lattice part, which corresponds to S, and nilpotent and rho part, which corresponds to the classical Springer theory. No, you don't. Of course, all of this should be taken up to isomorphism for simultaneous conjugation. Yes, of course. Okay. Right, so now let's consider some examples of this, like how this works in some explicit cases. So example number 0 is when q is equal to 1 and our nilpotent element just corresponds to the open orbit, so to the regular nilpotent orbit inside the nilpotent cone. Then BE is just a point, and of course what we just get the trivial representation. Let's consider example number 2. Again, to be like very explicit, let me again assume that q is equal to 1. And now let E be subregular nilpotent orbit. And let me recall that subregular nilpotent orbit is the following. So you take the nilpotent cone, you delete the open orbit, and then here you always have a dense open orbit, which is the subregular nilpotent orbit. And in this case, how the picture looks like, so yeah, let's describe the Springer fiber in this case theory, like the module that we get from this abstract description. So what we have? We have our nilpotent cone N, and we have orbit of the subregular nilpotent element, O subreg. And here we have our nilpotent E. And then what we can do, so and over this we have N tilde resolving the whole thing. And what we can do, we can now consider the slice to E inside N called Slodevy slice. So again, this works in general for arbitrary E. So I will denote it by SE, and it's defined as follows. You take the intersection of E plus the centralizer of F inside G check with the nilpotent cone, where F is a part of the SL2 triple containing E. EFH is a SL2 triple. So you have this slice to this nilpotent orbit, and then you can take the preimage of this slice. You get SE tilde. This is called a Slodevy variety. And this works in general, but in the case of subregular nilpotent, we get something two-dimensional. So we get a resolution of some two-dimensional singularity, and there is a theorem due to Slodevy that this resolution is precisely the Kleinian singularity resolution. Namely, this SE is A2 mod gamma, and this SE tilde is A2 mod gamma tilde, some iterated blow-up. And gamma is what? Gamma is a finite subgroup inside SL2C. And this finite subgroup corresponds to the unfolding of G check. So for example, if G check was type A, then you will see just Z mod N Z, actually naturally on A2, hyperbolically. But in general, gamma will be something that corresponds not to G check itself, but to its unfolding. Let me draw the picture. So namely, if you have, for example, G check being type C, then this G check tilde will be the following thing. You double the long root. So this will be type D, simply laced. And so what you see here, and yeah, let me also give an example of G2, of course. So in this case, you get like this, right? And so what is important? It's important that, so you see, the variety itself really depends only on this like simply laced unfolding. But the group which acts on this variety depends on G. Namely, this group A of E, I mean S is equal to 1 here, will be sort of automorphisms over G check of G tilde check. And explicitly, so in this type D story, you have these two vertices that you can swap. And this automorphism acts on your variety. But you see this automorphism only if you consider this variety corresponding to C as this ZE inside. And for example, in this case, you will get the action of S free. Okay. So this is the picture of subregular nilpotent. So you basically see this Kleinian singularity with this additional automorphism information. Now, to be very explicit, let me give you the answer, like which module you get. And of course, this will be very simple. And I will give you the answer in simple A situation when we don't have this automorphism. But you can generalize it. So now if G is ADE, then this Springer fiber is literally just a collection of P1s labeled by simple roots of your diagram. And of course, this K theory that you get as a module over W hat will be just, I denote it by H tilde, so it's just a Cartan plus CK, where K is the central element in G hat, and this is the standard action of W hat on it, where when you think about your Weil group as a Weil group of G hat. And this identification, of course, so you think about this K theory as about span of structure shapes of P alpha i's, and you also have a class of point, and then these guys correspond to simple roots, and this guy corresponds to K. Okay? So this is one example of how this like Kazhdan-Lusztig theorem works explicitly. Okay, yeah, right. So then the simple module that we're dealing with will be just the quotient. So this is a trivial sub-representation, and H is a simple quotient. Okay, so now let me pose a question. So we have some description of irreducible modules. And we also have these collections of standard modules. So now, one question that one might ask is, can we say something about characters of these modules? So the question, can we say something about characters? And let me recall that like characters, so we should just take an element of H, and then we should map it to the trace of our module V. So the module is finite dimensional, so it makes sense. And of course, so this is just a map to C. This trace factors through the quotient of H by the commutator of H with itself, which is like zero Hochschild homology of H. So this means that basically there are two questions here. Question number one, can we describe this quotient somehow? How to describe this quotient that I denote by CH? And the question number two is how to describe characters, how to describe corresponding functionals to characters on this guy. Okay, and so the goal of the first part of the talk is sort of give some answer to this question. But before this, let me recall one like important piece of structure on this Hecke algebra that I will use in the first part of the talk and also in the second part of the talk. So this important piece of structure is a filtration on H. So I will start from this. But before, are there any questions? Okay, so our H was K theory of some variety, right? And this variety lives over the nilpotent cone. So there is a very natural filtration on this K-theory coming from this map. Note that everything, fiber product was over n. Everything was over n. So what you can do, of course, n is the union of nilpotent orbits. And now what you can do, you can consider the preimage of closure of this nilpotent orbit and consider its K-theory. So filtration will be labeled by nilpotent orbits and will be compatible with the closure order on them. And it is defined as the K-theory, again, equivariant with respect to the same thing. But now you take the Steinberg variety and take preimage of the closure of the nilpotent orbit. So, of course, via push-forward map, this will be a sub-space of this guy. But certainly, this will be a two-sided ideal. So you have a convolution action on the left and a convolution action on the right. So this is a two-sided ideal. Uh-huh.
So if I was working one categorical level or respective category, but then I could get this by taking beginning in structural sheet Suzuki, take convolution there by work factor.
So this filtration is actually on the coherent side.
I know, but I arrived at your story by beginning on the constructible side. This question, I arrived at your story by beginning the constructible side.
Yes, so...
Let me get the end.
sorry, yeah.
Beginning with, like, let's say, mixed module one Suzuki, take convolution, take work factor, take associated gradient, like the module.
So take which functor?
This guy's verb, you wrote some paper. It's just associated gradient, like a module function.
Okay.
Then you wind up with coherent sheets on each side you be, and then you wind up with this story. And then, so the end of my question is, so you were saying about this trace. Categorical level trace means you go to G mod G, and so here I go to T star, coherent G down T star G mod G, just by starting with the categorical side and applying this structure. Is that where we're going to end up? And T star G mod G, like basically what we're saying, something like that.
You will see, so what I will be talking about will be, of course, closely related to this paper by Nadler, Prekel, and Ben-Zvi, where they considered categorical trace for the affine Hecke category. And realized it using this sort of commuting variety pairs. So we will end up with variation of this. Namely, we will split we will see that their result, from what you will see later, you will see that their answer, when you pass to K-theory, actually splits as a direct sum of some pieces that you cannot see from their perspective. And exactly these pieces will be labeled by this. So you will see that by some, okay, so let me think. By some reason, this filtration will split when you pass it to the cocenter. But yes, of course, it's very related. Yeah, let me make a comment here that, of course, all of this makes sense for a affine Hecke category. You can consider, I don't know, derived category of coherent shifts which are set theoretically supported on this closed subset. So this will be categorical counterpart of this filtration. Okay, so this is a two-sided ideal in H, but defined like geometrically, right? So we use this geometric realization of H when we were talking about this filtration. And question is, can we define this filtration but algebraically, namely using our algebraic realization of H, without referring to geometry? So let me give you the answer. And this will already be a very deep theorem by Lusztig and Bezrukavnikov. So let me formulate it. So we have our H, and we have a standard basis in it. But we also have a canonical basis in H.
What was the question you were asking?
How to describe this quotient. So we have canonical basis.
Can you explain to me why the answer is going to be some future? In the categorical world,
I mean, I will give you the answer. And
Why isn't it pure? That's what I thought.
you mean why is not? So for example, you will see that it splits into the direct sum of pieces labeled by these guys. You can.
The splitting part is the.
Splitting part is non-trivial, yes. And then you can describe each piece. Yeah, so basically you get the categorical answer, but actually by some reason you get associated grade of it. And this is non-trivial. Yeah. Okay, so, right, so we have this canonical basis element, which is like the standard Kazhdan-Lusztig canonical element. And what we can do now? Now we can consider, so for every element W on W hat, we can consider the following filtration on H, which is defined as follows. So this is just the minimal C-based two-sided ideal in H. So namely what you are doing, you are taking some element of two-sided ideal in H which containing CW. Namely, you just take your CW, then you multiply it by some element of H, you decompose into the sum of into canonical basis elements, you pick those which have non-zero coefficients, and you go on and go on further and further. And you take all, you take all of them. So in principle, it's, so if you have just some arbitrary basis chosen, so this will be very stupid filtration. It will always like give you everything. For example, for these TWs, you will get just everything for any W. But it turns out that for this canonical basis element, you get something non-trivial. So what we can do, we can now say that W1 is equivalent to W2 if we got the same things for W1 and W2. C-based, yeah, I mean that this two-sided ideal must have a basis over C consisting of CW primes. So this is like a based two-sided ideal. So in principle, there are many.
Is that bigger than the naive?
Yes, bigger than the naive, because we want all canonical bases to form a basis here. That's why I'm saying that in general you will just get everything if you start from some arbitrary chosen basis of your algebra. Okay, so you have this like equivalence relation, and it gives you a decomposition of the W hat into the joint union of some pieces.
On this coherent side, is there a way that is there a treatment of name of canonical basis stuff?
They correspond to some irreducible objects in some exotic T structure defined by Bezrukavnikov. Yes. So you.
What corresponds to that?
These canonical basis elements. So to every, well, I plan to say this a bit later. So to every CW, you can associate some complex living on this Steinberg variety in derived category of equivariant coherent shifts on ST. And this complex actually will be irreducible object in certain particular T structure in this exotic perverse T structures DB call. On Steinberg. And they will form a base, so like all, so that is a bijection between irreducible objects in this heart of this T structure and this CW. And the class of this object in K theory will give you CW. And this TW more or less, when Q is equal to 0, they more or less, I mean, at least the gamma, the part corresponding to like T gammas more or less will correspond to this O gamma, roughly. Right, okay, so return to this, in this like purely algebraic way, we get some decomposition of W hat into pieces which are called two-sided cells, defined by Kazhdan and Lusztig. And they label another filtration on each. So now, of course, the statement is that these two filtrations are the same. But let me make a comment that if you want to compare these two filtrations, what you should do first, you should compare the sets which parameterize these filtrations. One filtration is parameterized by these two-sided cells in W hat. And the other filtration is parameterized by nilpotent orbits in G. No affine thing here. So formally, I have defined it for you here. Namely, we're saying that W1 and W2 are equivalent if they define the same filtration pieces. And now you get decomposition of W hat into equivalent, and each equivalent class is a two-sided cell by the definition. So maybe, yeah, if you're asking, let me give you, again, two examples when you can like literally describe these guys. So of course, one two-sided cell that I will later denote by C-reg, because it will correspond to regular nilpotent element, is just 1. Okay? But the other two-sided cell corresponding to subregular nilpotent element, you can describe it explicitly, but the answer is sort of already non-trivial. Namely, it consists of elements W in W hat, such that W has unique minimal decomposition. For example, you can take any Si, it lies here. Or you canถ้Si as J when I and J are neighbors in the Dynkin diagram. But if you write Si as J such that I and J are not neighbors in the Dynkin diagram, then it will not lie here because you can rewrite it as SJSI. Okay? And you can describe these guys explicitly. We will discuss this later. Okay, but now let me make theorem. So the first part of this theorem is due to Lusztig, and the second one is due to Bezrukavnikov. So the part one is actually there exists a canonical bijection between the nilpotent orbits on N and two-sided cells above. And part number two is that indeed, with respect to this bijection, the filtration, like geometric one, coincides with the filtration by the two-sided cells. So like CO, H. Okay, let me say a couple words about, like, both of these theorems are very complicated. Let me say a couple words about them. So in the theorem number one, sort of like the main ingredient that you use to prove this theorem is so-called asymptotic Hecke algebra, denoted by J. And how you should think about this algebra, this is a certain limit as Q goes to 0 of the affine Hecke algebra. So in particular, this algebra will not depend on Q anymore. And how you define it, roughly speaking, you do the following thing. So this algebra J, as a vector space, it will still be has a basis labeled by elements of the while group, W hat. And now how you define the products of them. So you sort of, so what you do. We had canonical basis elements. You can multiply Cx and Cy, and you will get some polynomials on Q as coefficients. This was in H. But now what you can do, you can sort of take only highest term of these polynomials in Q. This sort of corresponds to Q going to 0. So now in this J, Tx times Ty will be equal to the sum of gamma xyz, z, where gamma is like a highest term in this polynomial. And in particular, this algebra more or less from the definition, for this algebra, the filtration splits. And this algebra is the direct sum of GC labeled by the two-sided cell C. And what Lusztig does, he constructs an embedding from the Hecke algebra to this algebra J, to which we formally add Q. And then he proves that if you take Q, so this is the embedding in general, but it becomes isomorphism after appropriate completion. And then he proves that if you take Q generic enough, and then if you consider module over J, which is irreducible, some module L, and you pull it back with respect to this embedding, then what you will get the standard module, this K of BES rho. And in this way, you get a map. So, of course, every reducible module over J comes from a reducible module for some of this JC. Okay? So, to every L, you can associate a two-sided cell C. And in this way, we get a map from ES rho, from our triples, to the set of two-sided cells. And then one can prove that actually these factors through, so this S and rho are not relevant, and this just factors to this from this bijection. Okay, and like, yeah, so this is like how one can think about one. So you see that the main tool here is this J algebra. L is some irreducible representation of J. So every irreducible representation of J, since J has this decomposition, will actually be reducible over one of these guys. So they are like ultimately decomposed into pieces labeled by these two-sided cells. And then
saying that the big C has a projection with the ESP.
right. So previously, reducible modules over H were parameterized by triples. And the statement here is that if you take reducible over J and pull it back, so you obtain a module over HQ, you will get a standard module for some triple, ES and rho. And actually, this is the bijection between irreducible modules over, so there is a bijection between irreducible modules over J and the reducible modules over HQ. But irreducible modules over J already decomposed into pieces. Okay, so, all right. And like the part 2 of the theorem, let me just very briefly say that, so to see this, you need to use this categorification of the whole story due to Bezrukavnikov, claiming that, as we discussed, canonical basis element categorifies to some complex on the Steinberg variety such that the support of this complex lies in this Steinberg of W bar. So,
And to clarify, you mean if I take K here, I'll get the canonical?
yes, so namely CW is equal to the class of this LW in the case. Yes. Okay, so now why all of this is important for our story? So the following theorem holds, so we have this map defined by Lusztig from H to J, and it's true that the cocenter of H can be identified with the cocenter of J when Q is not a root of unity. And this means that actually so since this J is a direct sum of JC, this means that actually this guy is already the direct sum of the cocenters of ZE, where E is an important element. So this is statement number one. Using this identification, we obtain a splitting of the cocenter of H. But then the second question, okay, oh, sorry, JE. But the second question is the following. Okay, we have this decomposition, but how can we describe each of these pieces? So now it depends on this J algebra, not of H. And of course, as always, first of all, we need some geometric realization of this Lusztig's algebra to answer such a question. And this is first main theorem. I will state it here that this J algebra can be explicitly described as a K-theory of something, but let me motivate the answer for you. So again, we want some description of this algebra in the same, like geometric, in the same spirit as Kazhdan-Lusztig realized Hecke algebra. So, right, and what's the answer? So first of all, we do know that this J is the direct sum of, so it decomposes into pieces. So the first, the most naive guess would be to like take associated gradient of H, something like this. And geometrically associated gradient of H is what? You take the direct sum over E of K theories of the preimages, now not of the closure, but actual nilpotent orbits, right? You kill the boundary, so you get this. And of course, you can rewrite this using the G checks transitively on O as the K theory equivariant with respect to centralizer of E times C star of BE cross BE of the product of true Springer fibers. Okay? But what's the problem with this? And I mean, this is not the correct answer. This is not J, direct sum. And what's the problem? So problem number one, let me recall that J was independent of Q, but the C star action here is a so-called Kazhdan action. It's non-trivial on this guy. This is a problem number one. Non-trivial depends on Q. And the problem number two is the following. BE is not smooth. So this guy, it's not a unital algebra, non-unital. Because when you actually define the product here, how you do this, you think about this guy as about K-theory of equivariant coherent sheaves on the Slodovy variety, cross the Slodovy variety, supported on BE cross BE. And of course, like class of the diagonal is not, which is 1, which is not supported on BE cross BE. So you get something non-unit. And then it turns out that both of these problems can be resolved simultaneously. Namely, let me write the answer here. And this was conjectured by Xi and Chua. So you want to consider equivariant K-theory with respect to the same product, but here you should consider not BE cross BE, but fixed points of both of them with respect to the Kazhdan action. So let me make a comment that, of course, now C star acts trivially here, because we just took a fixed point. But another thing, now this variety is smooth. And why is it smooth? So BE lies inside SE tilde, but the fixed points of them with respect to the action of a torus which contracts the base to a point are just the same. So you are taking fixed points of a smooth variety, which are smooth. Say it again. Slodovy variety. Sorry? Tilde. It's a preimage. So you have Slodovy slice, which leaves an important cone. And Slodovy variety is the preimage of the Slodovy slice inside an important cone. It is always smooth. It's actually always the Hamiltonian reduction of n tilde by some unipotent group. So it's always small. Yeah. So that's the answer.
Sorry, is C star here the Kazhdan grading for the slow slice or the Kazhdan grading on G?
For the slow slice.
But so wouldn't the
Because when you hear what should you actually write here? You should write centralizer of E inside G check cross C star, right? And when you identify it with this product, you will see this Kazhdan action.
So, but maybe I'm thinking about this wrong, but if I just naively look at the spring of fiber above E, I would assume that was just all fixed points of C star. Like the whole spring of fiber above my representative would have been fixed points for C star.
So this is a fixed points of the Kazhdan.
So I would have assumed that VE C star is just VE. This is spring of fiber above E.
No. So C star action is non-trivial.
On the spring of fiber.
On the Springer fiber, yes. It corresponds to the action by H. Conjugation by H. In your SL2 triple. It's non-trivial. Yes.
Well, why did we go from fiber product to zero product?
Fiber, yeah, that's this step. You see? So you have preimage of nilpotent orbit, right? Equivariant K theory of the preimage of nilpotent orbit. Now G check acts transitively on O with the stabilizer of E being this. And now what's a fiber over E? It's just BE cross BE. Okay, so right, sorry. This is isomorphic to GE, to this piece of GE. So the whole G is the direct sum of these guys.
But the stupid product, what's the product?
Convolution. Yeah, absolutely. This is a smooth variety. So let me make a comment that the only non-trivial part of this algebra is in this equivariance, right? So if you forget the equivariance, this is just the matrix algebra. But the sort of problem and why this theory is very non-trivial is because, of course, the Z can be non-connected. And for example, you don't have any localization theorem. So it's not true that if you take a fiber over some element here, you will get a K theory of fixed points. It's even not true that you will get a K theory of fixed points invariance with respect to the centralizer. It's more complicated. So the whole non-trivial part is in this equivariance. Otherwise, you just would get the matrix algebra. Okay, so let me now formulate the statement about the cocenter, and then I want to talk about different thing, but which is closely related with all this filtration story. It's a central, yeah, let me say, so ZE, here it's enough to consider like a reductive part of ZE, so you just consider the centralizer of the SL2 triple, E, H, and M. Okay, so now let me state the corollary. And for like, to save my time, I will state the corollary in case of GLN, when actually this is like very simple, and just say that it works in general. So if you're interested, I can explain this. Namely, the corollary is about the description of this cocenter. So the corollary is, so let's assume that G is GLN. Then this cocenter will then be just the direct sum over E, so it's a decomposition of functions on the quotient of Z by itself with respect to the adjoint action. So just direct sum labeled by nilpotence of functions on TE, maximal torus inside the ZE, invariant with respect to the while group. And then this functional, like this trace functional on the standard module, in this sense is like very explicit. Namely, you have this collection of functions here. and you want to associate to them a number. And what you do, you have your E, so you pick the function corresponding to E, and you have your S, and you just evaluate E at S. But again, this is a very much simplified version of this theorem because we're all over GLM. So we don't have this like additional, all centralizer will be connected in this case. And in general, you should consider some locally constant functions on commuting varieties, so on. Okay, any questions about this? Because I wanted to also mention another thing related to all this. Okay, so now let's consider like one explicit example in this story, which will eventually give us some information about characters of certain vertex algebras. So again, we will use this filtration story. So we have our Steinberg variety, and as always, it lives over an nilpotent cone. And we can consider any open subset of N, which is G-check invariant. So basically just a union of nilpotent orbits. And we can consider the pre-image of this guy inside the Steinberg variety, right? And then what you can do, you can consider our like large module, okay, like the whole, like in this case, it's just a while group, a affine while group. You can add C star if you want. And then you can consider the restriction of this guy to the equivariant K theory of this open piece. So this is some surjective map. And again, this is just quotient by some pieces of our filtration terms, as always, right? So we literally just kill the nilpotent orbits, which are not lying in U. So this map is compatible with the canonical basis elements. Namely, so if you have your CW, then it will map either to 0 if the corresponding nilpotent orbit is not in U, or it will map to the canonical basis element here. So what I'm saying is that actually the whole story of canonical basis elements, it can be generalized to like arbitrary bimodules like this.
So what do you have a C star?
That's just because for my purposes I don't need a C star for later. But yeah, you can add C star here. And let's now make some sort of observation. So canonical basis elements, like one of the most important properties of them is that they remember the Kazhdan-Lusztig polynomials, affine Kazhdan-Lusztig polynomials. Right? So in other words, we can take the standard basis element and we can decompose it into the sum with some coefficients that I denote by MWV of CV. So these are so-called inverse Kazhdan-Lusztig polynomials, evaluated at 1 in this case. Okay? And now what we can do, but yeah, let me make a comment. Note that we decomposed T in the basis C, not C in basis T. And this corresponds to taking inverse Kazhdan-Lusztig polynomial. And now what you can do, you can take this equality and take its image here. Then what happens? So now these TWs, they don't form a basis here anymore, but they still act on this K theory. So you will get that TW act on 1 is equal to the sum, and here these guys will still form a basis here, but some of them will just die. So you will get the same thing but only CV such that the corresponding orbit lies in U survive. Okay? And now what is nice about this is the following. Now you can ask yourself, okay, but how can I compute the character of a G hat module corresponding to this V? So character at the positive level. So character V inverse applied to lambda. Lambda is some dominant. So lambda plus rho hat is some dominant co-character for the affine one group. And which coefficients you will see here. So you will see here literally the sum over W and W hat. Here you have -1 W V inverse. These coefficients, the same coefficients that we had here, times the character of the Verma module. So the point here, you see, you have this swap. So here you had T in the basis of C, and here you have L, which is sort of C, in the basis of M. They swap. Like the conceptual reason for this is that you have some sort of Cauchy duality between representations of G hat on positive and negative level. And like these formulas and this module that we're dealing with controls negative level. But here we're dealing with positive level because lambda is dominant. But computational corollary of this is the following. If you want to compute the character of this module, you actually don't care about, you only care about this piece. You don't need to make computations here. You can make them here. Okay, so because you see, so this V is fixed. And the only thing that varies is W and W hat here. And like surprisingly, this like stupid observation allows you to actually compute some characters of some non-trivial modules over G hat that I will explain. Using like very elementary geometry. Okay, so namely, so like, yeah, so yeah, let me just put it here. If we want to compute this character, then this is the same as understand two things. Understand how this W hat acts on the K-theory of G check, and here you take like Steinberg corresponding to union of nilpotent orbits which are greater than or equal than V. And you want to understand the canonical basis here. So these irreducible objects. And if you understand these two things, then you are good. Okay. Okay, so, right. So as always, example number 0, what happens if our V is 1? Then this guy corresponds to the regular nilpotent orbit, so U will be just O reg. And our K-theory here will be just the trivial representation of W hat. And the canonical basis element will be 1. And of course, in this way, you recover Weil-Katz character formula. And the second example, which turns out to be already, again, from the perspective of geometry, it's rather trivial. So the second example is, what if we take our V in W hat, sorry, yes. So V is an element of W in W hat, and you want to compute the character of the following module. So you take category O, you take a dominant representative, and you label your objects by W hat. So this lambda might be singular, for example. So it's not necessarily a regular block. Yeah, so the goal is to compute this character. And the point is that actually to compute it, like it's very important in which two-sided cell this V lies. And like this example number 2 is what if V lies in subregular two-sided cell? Then in this case, U that you should consider is the union of the regular and subregular nilpotent orbits. So in other words, the module that we are dealing with and the module in which you want to describe the canonical basis is the equivariant K-theory of this like Steinberg U. And of course, this guy has two-step filtration corresponding to these two nilpotent orbits. So you can restrict and you just get C. So this is a trivial module. And you also have a submodule, which is equivariant K-theory of BE cross BE. And in this case, BE is this subregular slotted variety.
How do I decide what U do I choose?
Yes, so if you take some V in W hat, then the U that you should choose is the union of nilpotent orbits corresponding to two-sided cells C, such that greater than equal than the two-sided cell for your V. Right? So you have this bijection between two-sided cells and nilpotent orbits. You should take the nilpotent orbit corresponding to V and all that are above, because you want open subset. Okay, so you get some module which is an extension of a trivial module, and this equivariant K-theory guy. And let me say that, like, if you want to understand this, more or less, you should just understand the equivariant K-theory of one copy of BE. So let me restrict to this case, namely, instead of considering the Steinberg variety, let me consider smaller module, which is the K-theory of the preimage of U inside N tilde. Just because the answer will be nicer in this case. So we have this guy that we want to understand. So we want to understand the canonical basis here and the action of W hat. And this guy is the extension of the K-theory of BE and the trivial guy. And the simplest case that you can see here is when G is of type D or E. So these are precisely the cases when this centralizer is trivial. And as we discussed, in this case, this K-theory will be just H plus CK. And this is trivial module. So we should obtain some W hat module, which is an extension of this guy and this guy. Are there any guesses for the answer? So this is like H plus, sorry? So this is like a module over W hat, the standard one. And this is something one-dimensional. So, sorry? Right. So what you get here is just H hat. So this is the Cartan inside G hat. And the action of W hat here is literally, I mean, this H hat is H plus CK plus CD. And the action here is just the standard action by W hat. But what's the point here is that, so the canonical basis here is also easy to describe. Again, this is the simplest case when we don't have any equivariance. So the canonical basis here will consist of class, as you expect, of the structure sheaf -1 shifted by 1, and also the structure sheaf of BE. But let me warn you that this BE is the schematic fiber over E. This is super important. In type E, fiber over E is reduced. Outside of type E, it's not. It has some components. And this is like important. When you look at it class in K-theory, you cannot consider reduced guy. You get non-reduced guy. And then the canonical basis here in these descriptions, it one becomes extremely simple. Namely, the canonical basis becomes just simple roots, alpha I. So this guy corresponds to finite simple roots. This guy corresponds to affine simple root. And this additional element 1, on which we should act, like this one, corresponds to D. And now, in this case, how you compute Kazhdan-Lusztig polynomials? You take D, your element in H hat, and you apply some element to it, W, or lattice element, T gamma. And you decompose and compute coefficients in front of alpha i's. Plus T. So you will get some quadratic functions in this case on gamma. And as we discussed, this is enough to extract the character formula of these guys. And yeah, so yeah, the theorem and this, we worked out this explicitly in subregular case. And like why this is interesting, might be interesting. So by some reason, by these computations, we get all irreducible modules in categories O for certain vertex algebras. So let me make the statement, and then I will give you examples of the formulas. But yeah, any questions so far? Okay, so right, so yeah, so like application. And again, so let me say that what I will say now is something that you know and I don't know. So namely, there is this 4D to D correspondence, which associates to a theory tau, superconformal theory, some vertex algebra, and the expectations here are that the character of this vertex algebra should be equal to the flavored Schur index of this theory. Maybe more naturally or more generally, characters of irreducible modules L over this vertex algebra should be some flavored Schur index of tau in presence of surface defects. The associated variety of this vertex algebra should be a Higgs branch of this theory. And also people do expect that the vertex algebras that come from physics, but please correct me, should be quasi-Lie, in the sense that this Higgs branch should be a union of finite set of symplectic Lies, finite symplectic Lies. And this property of being quasi-Lie implies some quasi-modularity of these characters, implies quasi-modularity. And in principle, there are like a lot of theories, and the one which is relevant to my talk are so-called Argyres-Douglas theories. So when you start from such a theory, then the corresponding vertex algebra can be described as follows. You have a universal vacuum module, which is just induced from positive part. And this universal vacuum model has a unique simple quotient that I denote by Lk of G. So this is also a vertex algebra. So this is the algebra that corresponds to this theory, again, for a certain level K. And let me say that as a module over G hat, it is always like the highest weight representation with the highest weight K lambda 0. And then one can study the category O for this algebra, Lk of G, which will be a subcategory inside the category O for G hat.
Who's G here?
G is
In the setting of this
it,
word, who's G?
It's the G that you would use to engineer this thing in like the class S way, I think.
So it's the G of the class F.
Yeah, it'd be pretty involved in general. Like sometimes you can get double algebras this way as well.
yeah. There are many algebras that you can get in this way. This is just
Yeah. There's several infinite values of them. They have a pretty complicated classification.
Yeah, right. So they're not just labeled by G. They're labeled by one agent.
I mean, yeah, it depends on, well, yeah, they're labeled by a choice of a P1 with one regular puncture and then one wild puncture. So whatever that is.
yeah. So yeah, let me now make a statement. So the statement is just, I mean, it came up just from computations. But there should be some general theory behind this thing that I don't understand at the moment. Relating these two-sided cells with annihilators of simple modules in vertex algebras. So the theorem is the following. So we take some particular level K, which I denote by minus B, where B is the following. So B is the maximum label for the fundamental coways. So for example, in types A and C, this B will be 1. In times B, D, and G2, this B will be 2. F is 6, you will get 3. E7, E8, you get 4 and 8. And let me say that when you do E6, E7, E8, or D4, then this B will be a check divided by 6 plus 1. So maybe for someone this number will be familiar. So if you do this level, and again, conjecturally, this should work in general for any level greater than or equal than minus b, but still negative. And again, the cases which I checked, because only in these cases we have a parameterization of irreducible objects in these categories O. These are ID, ADE, or G2, or B3. But again, should be true in general. You see that irreducible objects in the integral ones, so with integral highest weight, in the category O for this algebra, are all of them are covered by our character formulas. Namely, the corresponding W to all of these lambdas lies in this subregular cell. And actually you have more, you have like literally a bijection between these modules and the elements of subreg such that W starts from some Si and lambda level of lambda I on this K is B. Right, so in particular, this means that in these particular cases, for example, we can compute characters of vertex algebras themselves, which are supposed to be these flavored Schur indices of these theories at the negative levels. Note that all of these modules are singular. All lambdas that we see are singular. They are not in the regular block for the category O. They are not admissible. They are one level below. sort of. And so what I believe this statement should correspond to, it should correspond to the fact that for all of these algebras, again, there is some conjecture due to Peng Shan, at least I learned it from Peng Shan, and it claims the following. It claims that the associated variety of this vertex algebra can be described as follows. So, like when you compute it, you see the following answer. Like in type ADE, you see O mean, minimal nilpotent orbit. In type B3, you by some reason see nilpotent orbit of the short root. And in type G2, you see the nilpotent orbit of subregular. But then you look on all these guys, and you see that actually all of them are D, Barbosh-Lugan-Lusztig, Vogan-Spaltenstein duality, applied to the subregular orbit. And this D should again have something to do with this, like passing from positive to negative level. But again, yeah, I don't know. So the fact that associated varieties are this guy should be related to the fact that we can recover all of them from our computations. Yeah, and let me finish with like a formula here. So for example, if b is equal to -2 and g is dn or g2, so for dn, you see that the character of this vertex algebra at the level of -2, like normalized by the affine Wild denominator, is the following thing. And the funny part here is that this follows from this very simple computation with K-theory of BE that we did, which is H hat. So you get the sum over gammas, and here you get some linear polynomials in gamma times e to the power u t gamma minus 2 lambda 0 plus rho half. So theta is the highest root, and alpha 2 is the root corresponding to the branching point. And maybe more interesting computation for G2. So for G2, you see the following formula, that the character of this guy is equal to, so again, we have the same type of sum, but here some quasi-periodicities things appear. So you decompose gamma check as a sum of m alpha check short at long root. And what you see here, you see some function which is like periodic with period 3 plus 1 divided by 4. And again, from the general predictions, all of these guys should have some nice modularity properties that I don't know at the moment. Modulo 2, e to the power u t minus gamma lambda 0 plus rho hat. And actually this like period 2 and 3, they're not just arbitrary numbers, they are exactly orders of elements in the group S3. So recall that the centralizer for G2 was S3. So that's why you see these numbers here. Okay, yeah, that's it. Thank you.
These B are the boundary admissible levels. Am I correct?
I think they are not admissible.
But they're not the boundary admissible ones.
I don't know. Yeah, so by some reason, this level minus b indeed appears when you apply this v. I don't know why. Why this minus b? Why not minus b plus 1, for example?
So beginning of the talk was about the representation theory of standard stuff, like well-known algebra, not these more exotic things, right? So are you telling us that representation theory of more standard algebras are related to these more exotic? That's the story?
Yeah. So I'm saying that by some. So you see that these more exotic algebras, they are these like simple vertex algebras. They are quotients of universal vertex algebras. So modules over, so universal vertex algebras, the associated variety of them is just G. So something standard. And now you're passing to some quotient. And what I'm trying to say here is that passing to this quotient should, at the categorical level, correspond to considering smaller piece of like Hecke category. And there should be some statement, some general statement behind it. So maybe I didn't mention this, but actually this cell, so what does it mean that you consider category O for this simple vertex algebra? So this means that inside category O for G hat, you consider only modules which are annihilated by some particular ideal. And actually these cells, at least in finite groups, there is a general statement that if you live in the regular block of category O, then you can take two simple objects and look at their annihilators. These annihilators will be equal if and only if these simples lie in the same right cell. So here something similar should happen, but in the affine setting, because here we see affine cells in this story. And again, as Lusztig explained, there is a bijection between nilpotent orbits and two-sided cells. So you see now here, you take this more exotic object, you compute its characteristics variety, you see that this is something smaller than G. And at the level of computations, you see that when you look at irreducible modules over this guy, then they correspond to W coming from this subreg cell, which, so this is in bijection. Lusztig bijection sends this to this. So this should become, so this should be some affine version of the whole story in which vertex algebra should somehow be included. Yeah, again, I don't know the explanation of this fact.
So affine version of the standard category O story?
First of all, yes, so just affine. So yeah, statement number one.